Hey mathletes, what's up? It's Mr. Nolde here, your personal math coach. Today I'm coming at you with some examples of everybody's favorite, the distance problem. Okay, so here we go with example number one, everybody's favorite distance problems. So it's a couple of different ways to do these. I'm going to show them. I have 4 examples. I'll do some with subscripted variables and some with a table. So how about this first one? I'll show you with the table. So it says this guy Carlton, he walked 76 miles to the site of the battle, and he rode the rest of the way on a caisson. He walked 4 miles per hour, rode 15 miles per hour. If the total time of the trip was 8 hours, for how long did he walk? So I want to solve for how long he walked for. So one way of doing these is to say, well, let's see. I know that rate times time equals distance, or distance equals rate times time, however you want to think of it. So this would be one column, or one row I will put walk. The other row I will put ride, because he's riding. So I know the rate at which he walked is 4 miles per hour, and I know the rate at which he rode was 15 miles per hour. I want to solve for the time that he walked. So I'm going to put a T here. Now I know that both of these times totaled 8 hours. It says here he took 8 hours to walk the whole, or to go the whole way, walked part of it, rode part of it. So 8 minus T would add up to 8 here. And then just multiply across. Rate times time equals distance. So this distance is 4t, and this distance would be 15 times the quantity 8 minus t. Now, this total distance ridden and walked was 76 miles. So these two things together add up to 76 miles. So there's our equation to solve for the time walking. So I would have 4t plus 15 times this quantity 8 minus t, and that's going to equal the total distance of 76 miles. So I'm going to distribute my 15 right here. So that's 4t plus, let's see, 15 times 8 is 120, and 15 times minus t is minus 15, still equal to 76. I'm going to combine my like terms here. I have a like term of 4t and minus 15t. So when I add those together, I get minus 11t. And that's going to equal 76 minus 120. So 76 minus 120. So these are both negative numbers, but that's okay because I have a negative over here to divide by. So negative 11t equals negative 44. So that makes sense because negative 44 right here divided by negative 11 right here is going to equal 4. So I know that Carlton walked for 4 hours. I could also now find out how long he, rode for too. The time walking, say T sub W, I know the time riding would also be 4 hours because it was a total of 8 hours. And I could even find the distance that he rode. So the distance walking and the distance riding, I could figure out those both. So 4 times T, that'd be 4 times 4, which would be 16. And 4 times 8 minus 4 is 4 times 15 is 60. So those do indeed add up to 76 miles. So you can save the most time if you set it up to solve for the variable that you need, the time that he was walking. But just know that you can figure out every piece of this puzzle by doing it this way. All right, on to the next example. All right, so for example number 2 here, I'm going to use subscripted variables. If you've ever used a Saxon textbook, this is how it's introduced by Saxon. So I'll show that too, because different people like different things. So it says Prince Frog Face, that's a tongue twister, and Princess Fish Lips were 63 miles apart. So that's a total distance at dawn. Prince Frogface began the journey to the meeting place at 7 a.m. at 3 miles per hour. So kind of walking slow. 3 hours later, Princess Fishlips set out to meet him. If they met at 4 p.m., how fast did the princess travel? All right, so for all these distance problems, we're looking at a rate and a time. So the rate of, yeah, I like that color, but I'm going to change the thickness of what I'm drawing. So the rate of, I'll say F, R sub F for face, frog face, is given as 3 miles per hour. And the time of frog face, well, if we see that he left at 7 a.m. and they meet at 4 p.m., that's 9 hours, right, from 7 a.m. to 4 p.m. So I already know the distance of frog face is 27 miles. So at this point in time, no, I have to figure out both. So at this point in time, I know that the rate of, let's see, fish lips. I'll use L for fish lips. So rate of face, time of face, over here, and rate of lips, and then I'll do time of lips right under it. So time of lips. So time of lips is, she set out, let's see, 3 hours later. So she walked 3 fewer hours than he did. So her time was 6 hours, right? She walked from 10 to 4 p.m., I guess. So 10 to 4, 6 hours. So this is what we want to solve for. And I don't necessarily know what her distance is, but I could probably figure it out. If I know they went 63 miles, and I know that Prince Frogface walked 27 miles, I could figure out here that the Princess Fishlips, walked 36 miles. So just by doing this, a little bit of scratch work over here, if I had a calculator, maybe I would have used that. Not sure. So anyhow, the total distance is added up to 63, but I don't even have to set that up. I have enough information just right here to figure out what Princess Fishlips' rate was. So going to go ahead and write down rate times time equals 36. We figured out she went 36 miles because they covered a total of 63 miles. So if I divide both sides of this equation by 6, I find out that the rate of fish lips, was 6. So 6 miles an hour, that's kind of quick, isn't it? She must have been jogging to meet the prince. So in any event, this is how you would work one out that has uses subscripted variables like this. And like I said, this is popular in the Saxon series. Not the new Saxon, the old Saxon, the original Saxon. One of my favorite. All right, let's look at example number 3. All right, here's a third example to show you. A lot of times I just like to read these and then sometimes decide if I'm going to do subscripted variables or create a table. So let's check this out. It says at 5 p.m., Joey Sweetkicks zoomed off from Sayre. 1 hour later, Maria Fashionista zoomed off from Sayre in the opposite direction at a speed 400 kilometers per hour less than Joey. If they were 7,900 kilometers apart at 11 p.m., how fast did each travel? All right, so we know both of their times, so I think I would be inclined to set this up using a table. So I have Joey, and I have Maria. So Joey Sweetkicks and Maria Fashionista. So we know that rate times time is equal to distance. So I put this across the top when I'm building a table. I don't know, I want to know both rates. How fast did each travel? All I know is that if I say his rate is R, that her rate is 400 kilometers less. So that's R minus 400. Now the time is, you got to do a little careful reading here. Joey Sweetkicks leaves at 5 p.m. and 5 p.m. to 11 p.m. That's 6 hours of zooming. And let's see, Maria Fashionista zoomed off in the opposite direction at a speed of 400 less. So it was 1 hour later. So she went for 1 hour less. So rate times time equals distance. So Joey went 6R kilometers and Maria went 5 times the quantity, R minus 400 in quantity kilometers. So when I multiply those together, I know that my total here has to add up to 7,900. Because remember, Joey took off in one direction, and Maria took off in the other direction. So this is the distance of Maria. This is the distance of Joey. So this would be 6r plus 5r, 5 times the quantity r, minus 400. And altogether, this is 7,900. When they got to here and here, they were a distance 7,900 kilometers apart. So sometimes drawing a figure like this is maybe helps you, maybe not. It just depends. Everybody is different. But the thing is you won't know until you do a bunch of these. So here I go. I'm going to solve this equation right here, right before your eyes. So we'd have 6r plus 5r minus 2,000. Right? I just distributed this 5 is all. Still equal to the total distance covered of 7,900. And if I add my like terms here, I get 11r. If I add 2,000 on both sides, right? Switch the side, switch the sign. You can think of it that way. Then just divide both sides by 11 to figure out what r is. So 11 goes into 99 9 times, and so that would be 900. So Joey's rate up here, let me switch some colors again. Joey's rate is 900. And Maria, her zoomy thingy must have been a little slower because she was 900 minus 400. So she was 500. Now, the problem didn't ask, but I could also figure out the distance that Joey covered and the distance that Maria covered, right? So Joey went 6 times 900, so that would be a total of, let's see, 5,400 kilometers. And Maria went, what's 7,900 minus 5,400? So I could do some quick mental arithmetic here. I'm just writing down what I'm doing. But she went 2,500 kilometers. So this information was not asked for, but you just need to know that you could figure it out if you wanted to. So mathematicians, usually being lazy by nature, they'll figure out exactly what they're asked for and stop right there. So this is what was asked for. Okay, so that was example number 3. Let's get on to the final example. Okay, so at 1 p.m., Jesse left the roundup and began the 66-mile trip to Dodge City. At 2 p.m., 1 hour later, the marshal left Dodge City to meet Jesse. The marshal's speed was twice that of Jesse's, and they met at 9 p.m. All right, so a couple of things you could do is say, well, here is the roundup. I'll put R for roundup. And Jesse leaves the roundup towards Dodge City, which is over here. And then the sheriff goes this way. And at what time do they meet? So this is a problem that would lend itself to either one of the techniques I had shown you. But I guess maybe I'm partial to this one because it helps students organize and see where to put everything. So sheriff is, oh no, it's not a sheriff, it's a marshal. Whoops. Marshal. So the marshal. It's after Jesse. Jesse James, I guess. And I have rate, I'll just abbreviate this time, times time is equal to distance. So I don't know how fast Jesse was going, so I'm going to use R for his rate because I see that the marshal's speed was twice as much as Jesse's. So that's a 2R. And I also know the times, if I do a little careful arithmetic here. Jesse leaves at 1 p.m., and they meet at 9 p.m. So that's a total of 8 hours, right? 9 minus 1. And let's see, the marshal left at 2 p.m., so that's 1 hour less. So he went a total of 7 hours. So Jesse went 8 times R, or 8R miles, and the sheriff went 2R times 7, or a total of 14 miles. 14R miles, I should say. And I know the total distance here was 66 miles. So that's the equation I'm going to solve. I'm going to say 8R plus 14R is equal to 66. Like terms to combine right here, so that gives me a 22R is equal to 66. And divide both sides by 22, we get 3. So remember what the 3 is. That's Jesse's rate up here. I'll switch the colors. So Jesse because they want each man's rate of travel. So Jesse, well, he was 3 miles per hour, and the marshal was twice as fast, or 6 miles per hour. So that is what was asked for in this problem. Again, I could figure out these two distances, but since I'm not asked for them, I'm not going to figure them out. Why don't you do that to complete your chart, figure out those two distances, and that will help you to understand these distance problems a little bit better. Okay, so there you go, sports fans. A couple of examples, 4 examples to be specific, of the distance problems. So not everybody's favorite, but the more you do these, the better you will get at them. Remember, math's not a spectator sport. In order to get good at math, you have to do math. So if there's any other topics that you would like me to talk about, let me know down in the comments below. So that's it for today. Go ahead, please like the video, subscribe to the channel, and comment down below. Until next time, this is Noldy signing out.